Last time we began our discussion on Pohama hypergeometric functions. So we introduced a notation of this type. So consider k tuple of rational numbers eventually we always assume that bk is 1, and also several conditions. For example, a non-resonant condition, non-resonant. In fact, we have several non-resonant conditions. So non-resonant condition that j minus alpha I, beta I never gets integer for every I in j. I call rather alpha beta non-resonance. Alpha beta resonance. So later we discuss other non-resonance. For example, the difference between betas is not also integer, or difference between alpha is no integer, is not integer. Such kind of condition also we impose at certain moment. So such kind of conditions are also considered to be non-resonance condition. But at the very beginning, from the very beginning, I impose this alpha beta non-resonance condition. Okay, then after this notation, we introduced power series. Power series, that is f. I think that gamma functions, gamma alpha j, and the denominator we have factorial of beta j plus m, beta j, and then so every expression has meaning. That is, say xj beta j, they are not negative integers or non-positive integers. Okay, this z to the power m. Really, I think that's enough. Yeah, that is the notation. It's yes, begins from 0. That is a 1 plus something. Yeah. And so this series is this Pohama hypergeometric series. And it satisfies, so say a kind of minimal differential equation. Minimality may be different. So this definition, and Pohama hypergeometric differential operator is like this: z times theta product of k operators, first order operators, times z minus beta j, where theta z equals z times ddz. And the first proposition was that f this power series that is convergent in a unit disk. So this is one of the solutions. We have, of course, k different linearly independent solutions we expect. And the first one, so in fact we started from this series and looked for, then we talked about the algebraic variety for which this series can be considered to be so I can write it down. So what was it? Yes, we considered this kind of differential form on certain algebraic variety x to the power j, alpha j minus 1, 1 minus xj, alpha j minus beta j minus 1 times factor that depends on the differential parameter z, 1 to k minus 1 of xj. xj, so it ends here, parenthesis, yes, consider this kind of, it is some rational form on an algebraic variety. That is, say y to the power m equals xj power something, 1 minus xj something, 1 minus z, sorry, here I forgot to write minus alpha k. The variety I m equals some polynomial. So it's simply product of factors of this type. Rational form on algebraic variety with this type. So I don't precise it because it's a bit cumbersome, but it is always possible. So so this variety has our space has x has k minus 1, k minus 1 dimensional, and y k dimensional. That is, it is a k-dimensional space. That is, say, we shall consider. So this is k minus 1 dimensional. K minus 1 dimensional. Yes. I forgot to write dx1. Yes, of course. It's a differential form. So. K minus 1 form. So this is dimension k minus 1, and k minus 1 form can be considered as a cohomology of this variety. And so Vz say z, I don't know. So in fact, we can consider linear combination of change with complex coefficients. J run something and alpha j, so alpha j is be c and gamma j be some chain, k minus 1 chain, such that it be such that, so okay, C, gamma, say gamma, such that the boundary of gamma goes 0. This is a cycle, so consistent with change, some change, minus 1 change, and such that this boundary of gamma b is 0, that is a gamma chain, k minus 1 chain. Of here, in this sense. So, in fact, if we apply, so we can consider this kind of integral over k minus 1 dimensional. This is k minus 1 dimensional chain, and gets a k minus 1 form. So it gives certain value, and it is well defined on as integrals along these cycles. And in fact, this proof, from this proof, or somehow a bit work with show us that, in fact, we did it in the case of Gauss hypergeometric function. In the case when k minus 1 equals 1, k equals 2 case, we did it, this kind of procedure. To identify it with, so in fact this is an exact form, d of omega, no, in fact it is so what is it? Yeah, gamma is equal to some d of, in fact there's no need to put constant, non-zero constant, so there exists some k minus 2 form, so there is k minus 2 form, this is k minus 2 form, k minus 2 form here, k minus 2 form, rational form, and with that. Probably I posed this question in among exercise questions or homework for the case of Gauss hypergeometric function. Yeah, that is can be. So omega, in fact, this is an exact form. And that is, say, we can, by Stokes' theorem, we establish this identity that, in fact, this is k minus integration of k minus 2 form over certain k minus 2 k minus q chain, but it is homologous, 0 homologous, and 0 k minus 2 chain. That is, it is 0. So this argument works for every chain. That is, for every chain for every chain, for every cycle, gamma cycle, so k minus 1 cycle from h k minus 1 VZ C, k minus 1, first homology. This relation holds. That is say, so the D was this differential operator of so-called Fuchsian type, or in fact this is Pohama hypergeometric operator, Pohama hypergeometric operator. So it means that every period, so in every period integral period integral of this type, so we shall of course fix the differential form, but once we choose one differential form to be integrated, there we have freedom to choose cycles along which we integrate. We consider integration. Every period integral of this type is satisfies is a solution to hypergeometric equation, Pohama hypergeometric equation, hypergeometric equation, that is a D of alpha beta sum 0, solution sum. Okay. So for this series, we have chosen very special type of gamma that was constructed from every xz plane. We have chosen these two branching points, 0 and 1, and somehow we constructed. In fact, we have chosen. We consider this kind of chain 0 1 on xj, and we constructed k minus 1 cycle, starting with a Pohama cycle, starting from this. Maybe so it's symbolic. So Pohama cycle. But in fact, there is this factor, so the chain, the cycle can be related to this factor. So this was f alpha beta z. Construction of this series, was based on the integration along this cycles. So from 0 1, only 0 1 segment, interval type segment, interval type chain. So in fact, so this means that this differential equation knows quite well that up to a C vector space if you consider this kind of integral for theta, so gamma has been chosen from C model. So in certain sense, that rank of this rank C rank it can be smaller than rank over Z of with Z. Also, this question I try to draw attention in the homework sheets for the case of VZ. Algebraic curve. So in general, this kind of phenomena. So if we admit as coefficients equal complex coefficients, we have less. In fact, this is already vector space, so we dimension, but so this kind of phenomenon happens. Yes, in fact, in certain sense, this situation makes our work simpler than to work with this. So this is the reason why we look at certain moment for at least during this lecture. So the course we have only 3 lectures, including today, and we have no time to, or there is no I don't know the theory concerning this type of fact. So we concentrate ourselves on this C model. Okay, then today I'd like to explain Menin-Barnes integral representation of Pohama hypergeometric functions. Okay, so the first result is the following. That is, say, our initial Pohama hypergeometric series allows us to admit a representation, integral representation of the following form. So we come up K, gamma, and minus I infinity plus alpha. In the numerator I have this gamma function, and denominator I have k minus 1, in fact k minus 1, and denominator I have gamma minus s and minus z to the power s ds. What is this integration path? So these so I recall that this alpha zeta under, we consider this kind of integral under alpha beta non-resonant condition. That is, none of them coincides, it means that we have minus alpha 1, minus alpha minus 1, etc. Maybe I should write it. And also, say minus alpha 2, minus alpha 2 minus 1, and so on. So this kind of, in general, as we are considering periods of, if you considering periods of algebraic variety, these alpha beta are rational numbers. If you want, you consider them to be positive, alpha 1 and alpha k, positive rational numbers. And none of them, the difference between them never never coincide with integer. That is, say, never no pole, no poles. In fact, this entails the following remarkable property of this integrand function, that is, say, no poles of the denominator coincide with a pole of the denominator and the numerator. In fact, yes. So denominator, these poles of denominators, that is, say, a minus beta j minus plus z negative integers, isn't it? Denominator, I mean that denominator itself. And suppose only here k minus 1, and so it this condition alpha I minus beta j never be integer, in that numerators pole is of this form, isn't it? Alpha I plus I also the same range, yes. And they never so coincide because yeah, this condition under this condition this never coincide. That is, say, there happens no cancellation of pole. Of poles of the integrand. Maybe I can write. So let us denote it something like HS. No poles of HS. This meromorphic function has really these family of poles, that is so maybe I should have written not here. Okay, so you saw this. Yep. So the numerator has poles minus alpha 1, minus 1, minus 1, etc., minus alpha 2, etc., and also s equals 0, 0, 1, 2, positive non-negative integers. Okay. In fact, it may happen that if we do not want to restrict ourselves on the somehow this kind of situation. Minus alpha 3 can be positive, but we take this integration path integration path divides two types of poles, alpha G z plus z and S equals and Z. That is, say, I shall consider the integration path minus infinity, infinity somewhere very so. That has so these. Yeah, so 0. You see that on the left hand side, so on the left, and on the right. So the poles of gamma minus S are located right on the right hand side of this integration path. So this is the somehow the meaning of this notation, integration notation. And of course you can choose this integration path up to homotopy. Up to homotopy doesn't matter, so you can choose a bit like this. It doesn't matter at all, thanks to Cauchy theorem. Important thing is to gather only these poles. Gather these poles. Yeah. So so this is the definition of this integral, and the statement lies in the fact that, so this is also can be considered as a proposition, that the summation of residues, say, for S positive, isn't it? We want to have a series, power series, with S getting larger and larger to plus infinity. Plus infinity. That is, say, we shall consider poles at these positive integer points. So the proof lies only simply the calculation of the residues itself. Calculation of residues. So maybe I leave it. The proof it comes from the calculation of the residues at residue of HS function minus z to the power s. What does it do? S equals say m at point m. What does it do? So gamma residue of in fact minus residue because, so I should come back. So this integral equals to summation of residues this, and this integration path can be can be deformed homologously into 0, 1, 2, so these, and so direction is this, that is say clockwise, etc. So it is enough to consider a summation of residues at positive integer points, no negative integer points. So this is nice. So what is this? A residue of S equals M, and the only there are no poles from alpha 1 alpha j plus S part. Of course, the denominator contributes no poles because gamma function has poles and never has no zeros, isn't it? Huh? So from denominator we have no pole contribution, and then from numerator we have contribution like this, but we have we make somehow deformation of this integration path on the right hand side, so that the result coincides with summation of residues at these positive integral points. So at positive integral, gamma of what is minus S, minus S, that is minus, let us consider. So that is residue of t equals minus m, so the S, ds minus ds becomes dt, gamma t, yeah, equals, paying attention to the sign, not minus 1 to the power m plus 1 equals m. So if I do this, simply it will give you gamma function part will give you this, and others can be obtained simply by replacing this S by M. Or others are holomorphic functions at positive integral here. So times minus 1 minus z to the power m, isn't it? That's the result of the residue of this integrand at s equals m, and it will. You see that it really coincide with. So minus 1 to the power m cancels both of them, and the result will be this. Okay, so in this way you see that this Menin-Barnes integral representation for a series, for hypochromo series, is valid. But of course you can so this was a collection of residues at m s equals m, s is positive. But how about if we deform this integration path on this manner, so that you gather residues at minus alpha j minus 1, etc. Yeah, with negative integer shifts. So the answer is maybe yeah. Okay. So how shall I notation a bit different. Okay, so if we deform, so the possibility how it is that the deformation of this kind of deformation is legitimized is proven by evaluation of integrand function that decays exponentially as the imaginary part of z, s tends to infinity as the integrand hs times minus z to the power s decays exponentially. For fixed z. So for every z, this integral exists, and then you let z move and get a function in z. Okay, so now we can gather residues of s equals minus alpha l minus m of this m equals 0 to infinity. Yeah. The integration, in fact, this integration, the above integral, is a linear combination C-linear, some coefficients in complex numbers, a C-linear combination of the following residue of series, say series. And now I have a series that begins z to the power minus alpha l, isn't it? M equals 0. Time from something. M is increasing, that is, say, z to the power minus m times z to the power minus alpha l. Yeah. So this is a series that is convergent. In fact, The convergence is 1, radius of convergence is 1, that we can verify easily. That is, so convergence near infinity. Near infinity. So for the moment we maybe, yes, I need to impose condition of alpha non-resonant. That is, say alpha I minus, did I write it here or not? There are different non-resonant conditions that I need to, alpha beta non-resonant, alpha non-resonant condition. I assume alpha non-resonant condition. That is, say alpha I minus alpha j, nothing, none of them coinciding, nothing else admits integer shift between them. So under this alpha non-resonant condition, say that the what is this? This means that alpha 3 or alpha 3 minus alpha 3 minus 1 or minus something never coincides with alpha 2 minus alpha 2 minus alpha and so on. There is no, so all poles of the numerator are simple. They are all simple poles. To the let us assume that. So in this situation, we have exactly L1 to k. We have k different types of convergence series with yes, dominant factor. So the dominant factor, say z to the power minus alpha l, and alpha l's are different. All alpha l's are different, and that is so. Let us calculate. In fact, I write directly the answer. In fact, it's nothing but a calculation, and this one will play a role. I don't know whether I shall leave it. So, okay, I begin here. So let us consider this this kind of residues, this kind of residues that can be calculated up to maybe some also near infinity. I write so integrals residues at s equals minus alpha l minus L minus say plus some negative integer, yeah, can be written in the following manner. That is, say, e to the power minus pi I alpha L. In fact, yes, I need to put here minus 1 minus alpha L and z to the power minus alpha L, and the summation does other. It is, say, the denominator is very simple. Simply you put and at each alpha n minus m, you where is it? Yes, you recall this. You apply this residue formula and get the following result. That is, except L, number L, every these gamma factor will produce this, and maybe I can erase it. Yeah. Divided by m factorial. In fact, it comes from gamma minus s, and gamma to the minus s, and I put s equals this minus alpha L minus m. Then I get this. Okay, and z to the power m. Minus 1 to the power m cancel by the same reason. So what is this? What is this? Yeah. So this is the answer. And I have L runs from 1 to k. I have k tuple of minus, so minus m, of course, minus m, yes. K tuple of a series convergent near infinity equals infinity, characterized by these gamma function expressions. Of course, this can be translated into this Pohama symbol. Expression, of course, yeah. And the fact is that the following, in fact, we got somehow k different series, and the upshot is the following, that they, each of them satisfies Pohama differential equation, Pohama hypergeometric equation. And Pohama hypergeometric equation as order k, and we expect the solution space has C dimension k. So it be somehow C to the power k. That is, say, in fact, it is true that locally near infinity we have this kind of decomposition C of G, L, these functions, these L equals 1 to k. So these are linearly independent. For hypergeometric equation. Okay, so we got finally we got quite so this was z near 0, and this is near z infinity. Okay, so these two series are defined in different, so it says a convergent domain, but they are of course related one another. In fact, this one is so I wrote it. This one was, this integral means that the f alpha beta z itself. So it's analytic continuation from here to here is given by this linear combination of GL hypergeometric functions. So and our task is to calculate, to get exactly exact expression of these GLs, but the linear combination coefficients of, say. But as you see that you can do it, if you follow. In fact, it is realizable, absolutely, like in the case of Gauss hypergeometric functions. So yeah, simply you shall be careful about calculating the residues at each first order poles. So yes, here maybe it's useful to. In fact, delta alpha beta, this operator introduced near z equals 0, but this differential operator has global character in the sense that you can consider it be defined over P1, projective space minus certain branching points, eventually 0 and 1 and infinity. So d alpha beta was written like that, but if I put w equals 1 over z, that is a local coordinate for w 1 smaller than 1, and a local coordinate near z equals infinity. Yeah. Projection first. Then you see immediately that this becomes minus theta w plus alpha j minus, say, I can write in this manner to see easily the symmetry. Plus g. isn't it? So z dz equals 1 over w d 1 over w over 1 d. That is nothing but minus theta w. Yeah. So in passing to the local coordinate system near w equals 0, we simply need to change theta z by minus theta of w and get the same type of hypergeometric differential equation. Pohama hypergeometric. This is always Pohama hypergeometric equation, isn't it? Simply the rho has changed. Yeah, absolute symmetry. So this is one of the reasons why it is so. Such kind of symmetry possesses very specific type of differential operator, and Pohama is hypergeometric differential operator possesses this remarkable property that allows us to construct somehow global theory. Global in the sense that not only z around the behavior solution near z equals 0, but entire P1. And you see easily that this differential operator has so singular loci. Singular loci. The principal symbol of this operator, d alpha, say, is z times say is zeta times power k minus z. So z d zeta dz turning to zeta after Fourier transform, a Laplace transform, and you know quite well that the principal symbol with this form. So that is say z to the power k z. Where is that? Yeah, z minus 1. Z. Yes, z minus 1 to the power z to k. So principal symbol is this, the highest order term of this differential operator. That is say it gives you z k z minus 1 equals 0, or in a symmetric manner. That is say 1 over z, and that means that the singular loci let's say the differential operator itself is 0, 1, and infinity. Only 3. So w equals 0 corresponds to z equals infinity. Z equals okay. Now, so in fact, in this lecture series, I'd like to explain how the monodromy. Now the aim will be in coming lectures. Our aim would be to establish the global monodromy representation of the solution space. For the solution space, say, let us know, solution space. C vector space, so locally it is k-dimensional C vector space. That is the solution space. Representation of solution as a representation of rho, so fundamental group some fixed point. So this is this means that we have absolutely like in the case of Gauss hypergeometric function, the structure of the fundamental group is the same as in the case of hypergeometric function. It has only three three loops. So the fundamental group consists of loops that are avoiding these 3 points. So infinity, you look at on the every time you need what is this? No, sorry. You need to look at the singular point, branching point on your left. Yeah, if you go like this, you see infinity on the left. Yeah, this is the loops. L0. So this is and we consider somehow the group homomorphism, that represents this group homomorphism into GLKC. GL of solution space. So solution at Z0, say. At Z0. Somehow Z0 here is locally it has a structure of k-dimensional C vector space, and as it turns back, so after some groups like you can as many times turn around these three singular points, and finally come back to the initial point. You get but the result will be the same C vector space, but the analytic continuation of these. So each of these this kind of series, of course, it's different from the initial one. So it will give rise to linear transformation of solution space. That is, maybe it's better to write like this. In fact, it is. It depends on the choice of the basis of the vector space, this vector space. So our attention will be focused on the choice of basis, k-dimensional vector space of this C-linear, this k-dimensional C vector space. That will be our task. So, but before passing to global means that starting from this, you consider every kind of loop. You can like this, or turn on infinity and go back and so on, and any kind of movement shall be taken into account. But before analyzing the global monodromy, we should understand somehow local monodromy. Local monodromy. What happens if so you let the series solution, series, hypergeometric series, to follow a loop that turns only around 0, not others. What happens? So that is this, L0. So local monodromy yeah. So local monodromy. Monodromy around these three there are three, and the result. And so I formulate in the following proposition, characteristic exponents of the solution space are following as follows. That is, say at z equals 0, it has characteristic exponents 1 minus beta especially 1 minus beta k equals 0. That is, say f so this first exponent. It's z to the power something. Yeah. So this 0 corresponds to the holomorphic solution to the hypergeometric equation that was the initial series, hypergeometric series. Z equals 1, no, z equals infinity, that is in fact, z is infinity we have already calculated. We have already calculated, where is z to the power minus, here we have. So it is a collection of, say, if I consider 1 over zb, the coordinate, it means that, or minus alpha, okay. No, it doesn't matter, so let us use simply 1 over z as a coordinate, then it is minus alpha L. Yeah. And the most difficult one is z equals 1. At 1. At z equals 1, the exponents are the following form. Z at 1, I have k minus 1 integers, and the last one, most difficult one is this. Yes, so this is the most non-trivial result. So z equals infinity I have already mentioned here. As for z equals 0, sorry, minus 1, I forgot, this is not correct, minus 1. Yeah, sorry, yes. This operator is not correct, so d alpha beta has characteristic exponent, so as if, so z equals 0, that is, say, this part is very small, and this operator survives. That is, say, Frobenius method tells you the asymptotic solution is z to the power lambda theta z plus beta j minus 1 some operator, that is lambda plus beta j minus 1 this must be 0, and that is, say, this must be 0. That is, say, lambda equals 1 minus beta j, and j, one of these numbers, that is can be calculated in this manner. Yes, in this manner. That is it is written here. Yes, it is written here. Okay, so z equals 0 is easy, and z infinity is also easy. That is, they are symmetric in a certain sense. And z equals 1, at z equals 1, situation completely different. Situation completely different. There is no symmetry between 0 and infinity. You have no this kind of change of variable. That's reduces the story of asymptotic, starting with asymptotic around z equals 1 to some other branching point. Asymptotics around 0. There is no such reduction. So we need to calculate the characteristic exponent. somehow sincerely, without any, say, cheating. That is, say, consider a series. Consider a series that is so z equals 1 near exponent so to do this this operator let us write it down in a local coordinate w, that is z minus 1. That is, say, z equals w plus 1. Consider this kind of change of variables and transform this operator, this operator, into w, in terms of w. That is, say, z equals w plus 1, and dz is dw itself, but yeah. So before doing that, maybe somehow here I made a calculation of the highest term. That is, say, from that it follows that z to the power k, z minus 1, dz, dk. That is the highest term. The second k minus 1, k minus first order, so dz k minus 1, k minus 1. So this coefficient. How I calculate? Simply, so you see directly this expression that it is a polynomial in theta z, isn't it? Theta z. And k minus first order operator will have summation of alpha j, so that time summation of alpha j, where is it? Yes, that is, say, z times summation of alpha j 1 to k plus minus summation of beta j minus 1 that you can see and z to the power k minus 1. This is the k minus first order terms, and then later k minus two order terms, and so on, so on. Yeah. Okay, now I pass to the local coordinate around z equals 1. Then it will become w plus 1 to the power k w dw d k plus z equals w plus 1 summation of alpha j minus yes, and isn't it? So we are looking for power series in W like this, a W to the power rho, say, times a W, a M, W power M, isn't it? We are looking for such kind of power series expansion expression, and first we the rho exponent rho shall be determined. So simply A0, the first term is A0 W power rho, A1 W rho plus 1, and etc. And let us apply this operator to this series. Okay. Then we have the following result, that W plus 1 to the power K W rho minus 1, etc., rho minus K minus 1 there. So from here, W power rho plus W plus 1 summation. Let me simply write like this. This one like this, and this one like maybe like this. Beta size of beta minus K. I hope that I will not. And W plus 1 to power K minus 1 times. So here I have rho minus 1, etc. Rho minus K minus 2. Rho minus K minus 2. Yes. I took derivative W power rho K minus 1 time. So the dominant first term, that you can ignore higher terms in W. So the first term that appear in this expansion. And this expansion is, where is it? So the first term that appear is W to the power times it is W power, of course it is W power rho minus, I shall not forget it, minus K, and here I have W to the power rho minus K minus 1. Okay? W to the power rho minus K minus 1. That is, say, the first term is W to the power rho minus K plus 1. Others are higher order. Thus, let us gather the lowest order term, that is, say, W to the power rho minus K plus 1. Rho minus K plus 1. So rho minus K plus 1, the first one is everything. That's rho minus 1. Rho minus K minus 1 here, till here, yes. 1, so 1 is here, yeah. And Next he has, here I already have w power rho minus k plus 1. And 1 comes here, that is say, simply I gather alpha minus beta plus k, what is this, times, something, it must have rho, no? W, okay, sorry. Rho k minus 1, k times this, rho minus 1, rho minus k minus 2, till here. Of course, this one and this one has the factorial till k minus 2 is present, isn't it? That is say, equals rho minus 1, rho minus k minus 2 till here, and last one, rho minus k minus 1, here I have rho minus k minus 1, and this one, plus k plus alpha minus beta. So that is say rho equals, so rho equals 0, 1, and k minus 2 till here, and rho equals this. Rho equals minus k rho plus 1 plus alpha minus beta equals 0. That is say, it is exactly the expression that I have written here. So this is a calculation, and in the literature, for example, I don't know, according to Levinson, this kind of classical real analysis-minded textbooks, you find this kind of expression. As Pohama's cycle, and there is Pohama hypergeometric functions or hypergeometric functions. So it is almost impossible to say some structure or symmetry. As I have shown you that in making use of the theta z, in fact it is invariant with respect to torus action. Torus action lambda. That makes the story quite clear and absolutely necessary to understand the structure of everything. So it is the result of introduction of toric geometric mind into analysis, rather so one of introduction of spirit of algebraic geometry into the analysis, that I hope manifested, demonstrated somehow its power in this kind of argument. So how difficult is it to follow, to construct an argument without use of this kind of symmetry, without also toric geometry. Yeah. Okay, so today I finish here, and So our aim will be always the same to express this monodromy representation. So local representation, I got it. We established today, okay, here. And so we pass to the global monodromy representation in following lectures.